In this movie, we will discuss how to create confidence intervals around a point estimate of a population parameter. It's a mouthful, but let's understand what we are trying to do. Our objective is that we want to find out the underlying population parameters, whether they are mean or population proportion. But we often do not have access to the population. What we have is a sample. So we may get our sample mean, or x bar, and we may also get a sample proportion, p bar. And our aim is to use these sample statistics to get an idea of what the population mean might be and what the population proportion might be. So because we do not know for certain what the actual population mean or proportion will be, we will use our sample values, our x bar and our p bar, to build an interval estimate. So essentially, we look at our point estimates and we add and subtract a margin of error. And this can give us some of a confidence that the actual population parameter might be within that interval. Now, we might actually miss it altogether, but at least it's a good start, because right now we do not know what the population mu is, or the population mean, and what the population proportion is. So in general, as far as the population mean is concerned, the general form of the interval is our sample estimate, or our sample mean in this case, plus or minus the margin of error. So what the focus of this lecture will be to understand how do we get this margin of error. And then similarly for the proportion, to get the interval around the population proportion, we will use our sample proportion, or p bar, and then add and subtract a margin of error to get our interval for our population proportion. And to do this, we will make use of the sampling distributions that we've discussed earlier. Sampling distributions essentially are the expected value and the variance standard deviation of our sample mean, as well as the expected value and the mean and variance of our sample proportion. We know from the central limit theorem that our sample mean follows a normal distribution. So because it follows a normal distribution, we can convert our sample mean to its z-score. And z-score essentially is given by taking our x bar, subtracting it from its expected value, which is the population mean, and dividing it by the standard deviation of x bar. And we will first work with the case that we know the population standard deviation. Now, in reality, we may not know that. We'll look at the modification of that assumption. But as an initial case, we'll work with the assumption that even if we do not know mu, we know the sample standard deviation. So in that case, we can write our z-score for our sample mean as x bar minus mu divided by the population standard deviation sigma divided by root n, which is, this thing is also called the standard error of the sample mean. So now there are two unknowns here. Our z-score, we do not know what that is, and we do not know what our mu is. Again, our objective is to build an interval around the population mean. So the way out of this is that we will fix a value of z, let's say z1, and once we determine what the z1 is, we can now solve this equation to get an interval around the population mean. So again, let's say that z1, z equals z1. If that's the case, then we can kind of cross multiply our standard error, and we get x minus mu equals z1 times the standard deviation divided by root n. And rearranging these terms, we can write mu, our population mean, as our sample mean plus or minus our z1, which we have determined a priori, and times the standard error of the mean. So this expression, z1 times a standard error of the mean, is called the margin of error. So our confidence interval then is our sample mean plus or minus our margin of error. Now, how do we determine the z1? The Z1 is chosen based on what we call the confidence level that we want to have for the true mean to be in a given interval. And typically we work with 90%, 95%, or 99% confidence. 1 minus these confidence levels are called level of significance, or alpha. And we will state these confidence levels in terms of the level of significance. So if our confidence level is less than 95%, then our alpha or significance level is 5%. If our confidence level is 99%, our alpha, which is a significance level, is 1%. And these values of the corresponding z-stat corresponding to the significance levels can be found from looking at the normal distribution or from JUMP or from the distribution tables as well. So again, know that we are building, let's say, a 95% confidence interval. So we will have 5% of the area outside of a confidence interval. So we'll split that in half. Each tail will then be 2.5%. So the value of z that we'll look at will be corresponding to our significance level divided by 2. So for example, if we are building a 99% confidence interval, then our alpha is 1. And on either side, then we will have 0.5 and 0.5% for a total of 1%. And we can look at these values from the normal table. So if our confidence level is 90%, our alpha is 10%. So our alpha over 2 is 0.5%. So on either side, we will have 5% tails. So then our corresponding z value will be 1.654. So in the formula for margin of error, we will then replace this z with that corresponding value that we choose. A more common one is a 95% confidence interval. In that case, we will have 2.5% area on either tails. So our alpha corresponding to that will be 0.025, alpha over 2. And then our z value is 1.960. And this is what we did in this example, where we wanted to build a 95% confidence interval. So our tails will be 5%, alpha over 2 will be 2.5%. And then our z corresponding to that is 1.96. So whatever our sample value of mean is, we'll add and subtract 1.96 times the standard error of that mean, again, assuming that we know the population standard deviation, or sigma, and we can get our confidence level. So let's work with an example. Here we are told that the standard deviation of the weight of elephants is known to be approximately 15 pounds. So we know the sample standard deviation. And we want to construct a 95% confidence interval for the mean weight of newborn baby elephant. So our alpha is 5%, which means that our alpha over 2 is 2.5%, or 0.025. And then it says that we had 50 newborn elephants were weighed. So our sample size is 50. And then the sample mean, it also tells us the sample mean is 244 pounds. Now, it does tell us the sample standard deviation. We do not need this because we are given the population standard deviation. So if we know that, that is what we will go after. If we did not know that, we would have to then estimate our population standard deviation from our sample. And then we'll have to make some adjustments in the way we ascribe probabilities to this. So as we have seen, our confidence interval then will be our sample mean plus or minus our margin of error, which is x bar plus or minus. Now we have our 95% confidence interval, so our alpha by 2 is 0.025, and we can look at this table and we can just read off 1.96. 1.96 times the standard error, which is sigma divided by root n. So now putting these in numbers, we get our x bar is 244 plus minus 1.96 times our standard error, which is, as we saw, 15 divided by root 50. So 15 divided by root 50. And then doing these calculations, we get that our confidence interval, and the lower limit of that will be 239.84, and our upper limit will be 248.158. So this provides us a 95% confidence interval that the mean birth weight of a baby elephant would be between 239.84 pounds to 248.158 pounds. So this helps us build a confidence interval for the population mean given our sample. Again, the key assumption here is that we know what the population standard deviation is. Let us do one more example, and this time we will work with a data set. So let's say that we know that the cost to repair fire damage caused by fires from all possible causes was $11,389. We want to compare this to the cost to repair damages caused by fires resulting from careless use of tobacco. So let's say we have a data set. We have 55 observations. Each of them is the cost to damages or cost to fix damages caused by fires resulting from careless use of tobacco. We want to use this to build a confidence interval around the population average cost of fixing fire damages caused by fires resulting from the use of tobacco. And we will then compare and contrast this with the damages resulting from fires due to all causes. So let's also assume that we know that the standard deviation can be assumed to be 3027. So we will use this. If we use the method that we did before, we can calculate the sample average, and then we are back in creating the margin of error where we look at 1.96, which is the z corresponding to our alpha of 0.025 on either tail, and then we can multiply it with the standard error of our sample mean. However, we will actually, instead of creating this by hand, we will use JUMP to solve this problem because we already have a data set in JUMP. So there's a calculator in JUMP called confidence interval for mean. To access that, we will go to the help menu, then we'll click on sample index, and this will open up a dialog box like this. You can click on tools, calculators, and this time we will click on confidence interval for the mean. And this will ask if we have raw data or summary stats. We actually have raw data, so we can select this option. If we did not have the raw data, we could have used the summary stats option. So click on raw data, OK. And this opens up a menu like this. Now here's our raw data, and we could have calculated our sample average, but this dialog gives us a sample average. What it also asks us is if we know the sigma, which is the population standard deviation. So if I go on this menu, we know that a population standard deviation is 3027. We can go back to JUMP, and we can type this in here. We see we know the sigma, and it is 3027, 3027. Then it asks us what is our confidence level, and our confidence level is 95%. Our alpha is 0.5%. And this is where we could modify our confidence level. If we wanted to change it to 99%, we could have done that. If we wanted to have it at 90%, we could have done that here. And once we click, it creates the confidence interval for the mean for us. It says the lower limit are 18,300. The upper limit is 19,900. So if we wanted to change our confidence level, again, if you want to be more confident, let's see what happens here. I'm going to change it to 99%. Notice that our interval got wider. So the more confidence we want to have, the wider our interval is, or less precise it is. If we wanted to have a 90% confidence interval, then it'll narrow down because our z value drops. But our question said 95% confidence interval, so to 95%. And the lower limit for our mean is $18,300, and the upper limit is $19,900. So now the next question is, how does this compare to our fire from all damages? And if you recall, the fire from all damages, the population average was 11,389. And if we look at our data here, for our damages caused by fires resulting from careless use of tobacco, our lower limit is 18,300, our upper limit is 19,900, which is way more than what it is for all damages, a fire caused by all damages. So what this tells us is that the fires caused by careless use of tobacco are more expensive and result in, on an average, a much higher cost. And we can be 95% confident, given our sample, that this is where the population mean might be. So again, a very practical use of creating a population confidence interval for the population mean.